to business optimization in relation to the strategy of the traveling salesman problem. The traveling salesman problem is a well-known problem in business optimization and also in computer science and programming. Typically, it's a problem in which we have a entity, a salesperson in the basic example, who has to visit different locations at least once and wants to optimize on reducing the entire sum of distance or the entire sum of cost if we take petrol as a unit. It's a pretty straightforward calculation. However, the uniqueness about the traveling salesman problem is it becomes very complex very fast. So in a very simple example, we can take a graph on a map and we can approximate. This would be an approximation of distance. Instead of taking the real streets, we can draw a graph. Now in business optimization, if this is a new topic for you, it's very important to understand that a lot of these business optimization approaches rely on models, and models are abstractions of reality and usually simplifications of reality. So these simplifications in this case are that the distances are straight lines and not swirly lines and not accurate lines in terms of streets. But the abstraction is very important because based on these straight lines and based on a person who starts in Boston, wants to end in Boston and visit every one of these cities, based on this proposition or assumption, objective, better to say, we need to abstract the reality, and we do this with graph theory. So a traveling salesman problem usually uses graph theory. A graph is a mathematical structure that comprises of nodes and edges, and typically the nodes and the edges have values, and then we can do mathematical computations over it. So the traveling salesman problem is not just a problem in the area of business optimization or in the area of optimizing a route planning problem. It is also a challenge or a approach taken in network management, for instance, in computer science, where packages have to pass a network of computers, and what's the fastest or the shortest ways to do so. It's used in protein folding. It's used in a lot of different approaches and a lot of different sciences. This is just a brief introduction into this. So if we would imagine that we would want to visit every city in the US that has 500 inhabitants, then it's very quickly and very easy to comprehend that this would become very complex. So to visit every city at least once, we would need to come up with a very, very good strategy so that we don't waste time and we don't waste resources. So here could be a question: how to visit every street once. One typical example that is used in computer science, or typical approach, is just to randomly connect every one of these nodes on random and then start to optimize based on the random connections. And then basically every iteration, every new graph, every iteration that still connects all the nodes but in different connections in different ways, is then evaluated based on the sum of the distances with the graph before. So the random graph is most likely not the most optimal graph. Therefore, we pick additional graphs to see if the value becomes better. It was invented in the 1930s by a man called Karl Menger. He was a mathematician. It was discovered by him, but it's a very, very real problem, and still in 2024, it's a real world problem, and it becomes extremely complex. That's the problem. The complexity is exponential, therefore the growth is exponential. The more nodes are added to the graph, the more complex the challenge gets, the more computational power is needed. The permutations become very high. So if we take real streets, that's at the bottom of this text, the permutations are very high, and the permutations also mean that if you would have a graph of, let's say, 15 destinations, and you take all the streets that are possible between those destinations, if you take the US map, for instance, then you have 87 billion possible routes. So there's a lot of roads you can take, a lot of possible routes you can take, long ones, short ones, all kinds of routes, just to get to those 15 different destinations. So a computer can't know straight out what that is. So there's different algorithms that solve this. If we take a very simple example, we want to get from A to B, and there's two routes to go. So if we take tools like Google Maps or Apple Maps, and these tools typically calculate the shortest distance or the shortest time, They also take traffic into account. They also take elevation into account. So the model can become a lot more complex than just distance. But in this case, it's very straightforward because we're just comparing two routes, and we just take the route with the less time and also with the less kilometers. However, if we add a lot more to the graph, if we abstract this and add a lot more to the graph, then it becomes more complicated. And it's pretty easy to see how this works. If you start in one and you have to end in one and you have to hit every one of these nodes, then you can manually, with this very simple graph, you can just manually say, okay, we go from 1 to 2, from 2 to 3, 3 to 4, 4 to 5, 6, 7, and back to 1. Or we could go 1 to 3 and then 2, 4, 6, 5, 7, and back to 1. So there's a couple of different graphs you can come up with here, and you basically calculate the sum of each one of these round trips, so to say, and you'd pick the one that has the minimum distance. One strategy is the so-called greedy algorithm. The greedy algorithm is an algorithm that is used a lot in computer science. It's a very simple algorithm. In graph theory, you pick basically always the path with the least or with the most reward. In this case, because it's an optimization challenge on time, on resource, we pick the path with the least resource. So we go from A, we go to B, because from A to D is 35, from A to C is 42, A to B is the cheapest, so lowest value. From B we then continue to go to C, because again that's the cheapest, lowest value of a not taken path. C we go to D, and D we go back to A. So very easy, very easy example. The problem with the greedy algorithm is, or problem with this kind of algorithm is, it doesn't really look ahead and it doesn't really have a memory. So you can get into these so-called you can get into these kind of traps, or into these local optimums where the greedy algorithm takes us down the graph and suddenly gets stuck in a part of the graph where it can only get out again by following very high values, and those high values might have been avoided if the algorithm would have looked ahead or would have used a more sophisticated algorithm. So I think at this point you should be clear on how easy this becomes very complex and how complex this problem is. So the main challenge is to get from a given location to all the different destinations, to basically visit them once and to go back to where we started. And the complexity is to know what the best route is. And this traveling salesman problem, again, has a very high complexity. The more nodes you add, the more problems ensue, because then obviously you can end up in a part of the graph where there's a lot of local problems, where the values are maybe too high and you can't get out of it. And if you would have known that before, you maybe would have taken a path with lower values or different values. Or you might have would have sacrificed early and would have said, okay, I'm taking a very high value at the beginning, a very high path at the beginning, because I know if I get there with a high value, then there's lower values and higher rewards down the algorithm, down the chain. So we need to understand these things, and we understand these things by generalizing. So this is a very, very simple, high level way of looking at it. We can then also transform this into a table. So once we have a graph, we can switch this to a table with the distances from A to B, A to C, A to D, B to A, B to B, B to C, and so forth. And once we have this graph, we can simply build a mathematical equation on it. We can build algorithms on it, and there's hundreds of different algorithms. There's very interesting algorithms. One called the African water buffalo problem, where water buffaloes travel from water hole to water hole, and they do that in a very optimal way. They do that intuitively. So some teams have extracted algorithms from this behavior, from the animal world, from biology. So there's some really interesting algorithms. Another one is a brute force algorithm, where you basically just check all possible routes, and then you just kind of keep rejigging the graph and picking the one that has the smallest value. That's the most expensive one, and very expensive in terms of time and resources. A more clever one is the nearest neighbor, where you basically you pick paths where you can go for local optimums, because you always follow the nearest neighbor solution, and if there's no nearest neighbor, you go back again and you start taking different paths. In this presentation, there's no algorithms. This is very simple, high-level presentation, but there's a lot of very sophisticated explanations on YouTube if you want to go deeper and actually calculate one of these.